Cool. Thank you, everyone. So the title of my talk is obviously a little bit of a joke, but hopefully the rest of the talk won't be. So the flying spaghetti monster is the deity of a joke religion, Pastafarianism, and it's arisen, I think, in 2005 or something like that, as part of a satirical response to discussions about intelligent design as a philosophy versus natural selection. I think it actually makes quite a nice mascot for conversations about distributed system and software because, I guess, unlike the real world, we don't get to go one way or the other with intelligent design and evolution. Like evolution, especially in microservice architectures, is a fact of life. We cannot, even in our wild architecture, ivory tower fantasies, live in a world where the single mind conceives of a whole system and that's just it. On the other hand, we do need a bit of intelligent design because unlike natural selection, we can't really tolerate countless deaths in a way to get to kind of the design that we want. So the conversation I want to have with you today, I'm going to use Idris as the medium. So Idris is a hipster programming language. It has static types. It's functional. So if you're familiar with things like Haskell, with F#, with Scala, you probably know a bit about it. So like those languages, the compiler checks the type. So it's not a dynamic language. It's in fact one with a very expressive type system. It's also one where functions are first class. And that's probably not something that's very surprising to this audience. We've kind of got to the point in the industry where the idea of functions being passed in as arguments, being returned, being calculated upon is just par for the course. But the feature that Idris has that not all these other functional programming languages do share is that types are also first class. So by that I mean types can also be passed as arguments, can be returned, and calculations can be done on types. And that might seem at first to be a slightly weird idea. I think probably first-class functions may have seemed like a weird idea the first time some of you saw them. But it turns out that it's actually a great simplification to not have to treat the world of types and the world of values as distinct worlds. So once you get used to it, I think you'll actually find that it's a simpler model of understanding programming. And maybe just like with first-class functions, if you do end up getting used to it, you might wonder what the fuss was ever about. So you have the pleasure today of hearing a talk potentially by one of the great experts on Idris in the world. His talk is at 4:20 this afternoon. His name's David Kristensen. I, on the other hand, am a great enthusiast of Idris. So I think that it's a really interesting programming language. It's really helped me understand the kind of the nature of types and proof to a much greater extent than I did before. If you are like me and you want to become an enthusiast about it, this book is a really excellent book on programming in general and Idris in particular. So just like I would say all great programming books, it starts with a specific subject matter, so how Idris works, how dependent types work, and broadens it to become an actual philosophy of development. So it does explain how you evolve a program with expressive types. It gives you hints with how the editor works and just how your workflow works. So if you're someone who is, like me, quite enthusiastic about this, but isn't necessarily deeply steeped in the academic work on the subject, I really recommend this book. So the motivation for my talk is, as Bodil kindly pointed out, microservices. So I'm going to start with my kind of cottage definition of microservices. Because I think one of the big problems with conversations about microservices is definitional, right? So it is a buzzword, right? Everyone talks about doing it. Everyone means something slightly different. So the way that I would define microservices is that by their very nature, they're about shrinking or abolishing transactions on many different dimensions. So the obvious one is at runtime, processing data. So if you have a cooperative set of microservices responding to a user's request, perhaps some things operating synchronously, other things operating asynchronously, then you're actually dealing with a series of events rather than one big transaction that you might in a monolith. You can also change code a little bit at a time. So you could see this as a transaction in the evolution of your system over time. If you have a monolith, you can change everything in one go. You can add an argument to the function. You can add an argument to all the callers of that function in one transaction, one deployment. In a microservice architecture, that's not true. And finally, you can understand systems a bit at a time. So the human factor, the ergonomics of microservice architectures makes a different trade-off. The idea is that each piece becomes simple to understand. So my colleague James Lewis, who talks about microservices, jokingly says the right size for a microservice is something you can fit in your head. So it's not just a division based on technical concerns, but also the human factors. But whenever you get rid of or shrink transactions and do things across transaction boundaries, you've therefore accepted the burden of having to coordinate, of having to manage the eventual consistency. So you're going to have to deal with partial failure. What happens if one of the bits of the data that you're processing succeeds and others fail? You're going to have to deal with what happens when you have an ecosystem where people are on different versions of the JVM or different versions of programming languages. And you're going to deal with the fact that while you've broken things down so they can be understood one piece at a time, you still need a way to zip that understanding back up into an understanding of the whole, which is, I think, the biggest problem that I encounter at the moment. So this is one of my favorite pieces of programming folklore. Any sufficiently C or Fortran program contains an ad hoc, informally specified, bug-ridden, slow implementation of half of Common Lisp. Now, on the surface, this is kind of a puerile like language wars thing, so I definitely don't want to engage with that. But I think the underlying point that Greenspan is making is that if you incrementally evolve a system, adding complexity over time, unless you achieve breakthrough abstractions in how you organize your thoughts and how you understand them, you're going to end up in pain. You're going to end up with a problem. So I see this as a way of talking about computer systems and having to bridge the gap between that evolutionary angle and the intelligent design angle. If you don't come up with a way of thinking about it, the equivalent of the Common Lisp abstraction, you're going to kind of just incrementally get more and more spaghetti. And I think that applies to microservices very strongly. So any sufficiently complicated microservice architecture contains an ad hoc, informally specified, bug-ridden, slow implementation of a distributed protocol. Right? And that, I think, is a problem because distributed protocols are hard anyway. You know, understanding how Paxos works is kind of a proverb for, you know, straining your intuition. Yet this architectural practice, which we do for very good reasons, puts a lot of extra burden on our ability to understand distributed protocols. So we're actually, in a way, playing to our weaknesses here. If we don't achieve these breakthrough abstractions, these better ways of thinking about things, then we're in trouble. And I'd say that narrative is not enough. So I think that industry best practice, or just kind of standard, I use best practice kind of skeptically, is that when you're being taught about how microservice architecture operates, it's done through narrative. Someone sits you beside a whiteboard and tells you the happy, potentially fictional story of a good request who gets everything they deserve and has a happy ending. And that's a great and important part of communicating information as developers, but it's not enough. And I think probably companies that do this really well, they kind of have non-fictional narratives as well. So really good observability is also a very important way of keeping a handle on the complexity of a microservice architecture. But I don't think pure narrative of just what stuff happens after what is enough to get us out of this hole. So one example of an actual useful abstraction at the protocol level is finite state machines. And when I'm talking about the protocol level here, I'm talking about application protocols, so not TCP IP, although they can also be abstracted with finite state machines, but the kind of protocols that are about how the bits of your system that you've designed bespoke operate together and cooperate to achieve your business goals. So finite state machines can model protocols. It might be something that a few of you are already familiar with. I just put this comparative picture up because as I was Googling for FSMs of diagrams of finite state machines, it struck me that just literally the structural similarity of both this flying spaghetti monster and an ordinary finite state machine was kind of striking. So a finite state machine is a system where you have one or many meatballs that represent states of your system and strands of spaghetti that connect them together that tell you the legal transitions. So in this particular case of the door, you can open a closed door, you can close an open door, you can knock on a closed door, but for example, you cannot knock on an open door. Right? That's something that's not allowed by this protocol, this abstraction. Finite state machines aren't as expressive as general purpose programming languages, and that's a good thing because the less expressive your abstraction, assuming it meets your needs, the easier it is to reason about. So if you can have a slightly simplified model of computation, if your protocol can fit into finite state machines, that means that it's easier to reason about. There's less of a burden on the reader. So in our programs, we often do actually have finite state machines, whether or not we model them explicitly. So this is a little bit of, I guess, kind of pseudo JavaScript that works with that door. So first we open the door, then we knock on it, then we close, right? And if you're paying close attention to what is legal with a door, you might notice that this is actually an incorrect program, right? We open the door and then we knock on it. So in the case of really egregious type errors, so for example, if this snippet of code had a method that did not exist, that would actually be something that's quite easy to detect using normal methods. Your unit test would crash in the middle of it or something like that. But when we're talking about incorrect sequencing, even ordinary or naive application of type systems isn't sufficient to capture that. But there are ways of doing that. So there is a technique developed by Bob Atke called Indexmonads. I prefer to think of them as domonads. I guess you can kind of like, you've got monads, comonads, domonads, because the key element is that they track the state at the start of the operation and the end of the operation. So a door session is a data type in Idris, like we're calculating types here. It's an algebraic data type. So there are 4 ways of making a door session. You can have a knock action, and a knock action takes your state from closed to closed. You could have a close action, which goes from open to closed, and you can have an open action that goes from closed to open. So each of these actions has 3 type parameters, 1 for what the action returns, and 2 for the start and end states. What the bind, that kind of double chevron equals thing at the bottom does, is it applies the domino rule, right? So if you place dominoes in a line, you have to make sure that the number on the end of the domino matches the number on the start of the next domino. You have to line it up like that, because that shows you that you're legally progressing through the finite state machine. So if you see just down the bottom, you've got knock, close, and open. It's kind of a domino representation. So if you're not familiar enough with that kind of static functional programming syntax, just think about it in terms of the dominoes, and you'll have the relevant bit for this talk. So if we try to render that incorrect program we saw earlier where we knocked too late, that will be a compilation error in this particular case. So the dominoes are lined up down the bottom. We started in a closed state. We opened it. So we went from a domino from 1 to 2, and then we tried to knock, but that breaks the domino rule. And because in this case the compiler is enforcing the domino rule, it's able to tell that this is an incorrect program. So if we did do it though, write correctly, then we've got the green there, the domino rule is obeyed. We've knocked first, so we've gone from closed to closed, then we've opened it, closed to open, and then finally we've closed again. So we've got where we need to go. We've traversed our way through the finiteness state machine without breaking any of the rules, and in a way that the compiler is able to check. So Indexmonads are quite useful for this. So there is a concept that I've heard that I think is a fallacy, especially in microservice architectures, that I want to, I guess, talk about, which is that if you have a network boundary, it makes the idea of type systems irrelevant. So I can see that's kind of a seductive concept, because types, to some degree, enforce what's going on in your own program, and then as soon as you get out into the wide world, you could say, well, you know, what help is that? But I think it's actually not quite true. So what I'm going to do in a kind of, guess, time-honored rhetorical fashion is I'm going to set up 3 straw men, and then I'm going to spend the rest of the talk, I guess, knocking down my own straw men. So forgive me if that seems self-indulgent. But first of all, you might say that types can't help you because of fallibility. Right? If a type is about everything happening in the right order, just like my earlier example with knocking on the door, then when things go wrong in the real world, doesn't that mean that, you know, we're outside the type system, we're off the reservation, nothing is going to be checked anymore? Distribution is another problem. So if I do have these kind of like cast iron mathematical guarantees, how do I make sure that everyone I'm working with has them? There might be other teams working other parts of the system. There might be people evolving systems over time. How do I actually distribute these protocols in a way that we can consistently have a common view of it, other than narrative and whiteboards? And reciprocity is another interesting one, because when we have these protocols across systems, people aren't all playing the same role. So you need complementary interactions to get to the right place. You can't just distribute the same kind of series of actions and expect everyone to do exactly the same thing. They've got to cooperate. Before I get into just the knocking down of the straw men, I wanted to go back to this picture of the flying spaghetti monster, partly because I think it's a work of genius. If you're familiar with the ceiling of the Sistine Chapel, this is a Pastafarian version of that. But the bit I wanted to call attention to, this time when we go back, is the white space between the flying spaghetti monster an atom. Because I think that actually that detail in this painting, well, definitely in the Michelangelo original, but also here, is the really interesting poetic part of it. So they're not touching, right? They're interacting, they're trying to communicate, they're trying to reach an understanding, but there is a gap between them, an unbridgeable gap. There's always going to be some room for the network to get involved or for there to be human misunderstanding. So regardless of how well your states in your flying spaghetti monster implementation work, you always have to deal with the fact that there will be misunderstanding and that you don't have that omnipotent control over your system. And I think that's what is going to distinguish successful type applications to the network from unsuccessful ones. That if you see types as a way of controlling everyone else so they don't do the wrong thing, that's not a successful philosophy. What you need to think about types as is a self-discipline so that your system does the right thing regardless of when things go weird or things go wrong. So it's a way of making sure that you've done everything you need to do to be robust in an uncertain world, not about imposing your will on other parts of the system, which I think is actually a kind of an ivory tower architect philosophy that just doesn't work in a rapidly evolving system. So first, fallibility. So this is really important because failures happen in all sorts of ways. So this is the first sentence of Anna Karenina by Leo Tolstoy, that every happy family is alike and every unhappy family is unhappy in their own way. So you could apply that to requests, the Anna Karenina principle, right? So a successful request might follow that simple path, and that's really easy to whiteboard, really easy to unit test, really easy to system test. It's the multitude of combinatorial unexpected failure cases that really makes this hard. So a simple way of incorporating failure into our finite state machine model is to have non-deterministic state machines. So in this particular case, and I've borrowed this from Edwin Brady's book on interest, the door, when we're trying to open it, it might jam. So we try to open it. We can't assume that that's happened because this might be a literal door that we're interacting with. It might be, an Internet of Things enabled door in our living room. Maybe the battery has run out. Maybe there's something in the way. So we have to deal with that circumstance. So at the finite state machine level, well, we can draw that. And it turns out that at the type level, we can also account for this with a little bit more subtlety in how we define our types. So in this model, which is a bit more sophisticated of the legal types of a door, we can still construct the door session by knocking. But what happens is we go from the closed state to another state determined by a function of the result. So that exit state is no longer a constant value, it's a function. So in the case of knocking, we always end in a closed state. So just constantly return closed. In the case of closing the door, well, we always assume that succeeds in this model. So that is the constant function closed. But for opening a door, this is where we get a little bit more type foo. The door session of opening returns a bool. It starts in the closed state, and depending on the result of that bool, whether it's true for successful or false for unsuccessful, the exit type will be either opened or closed. So we're actually, I said earlier that we had first-class types, so we're going to do calculations in our types. This is an example of where we've actually baked into the type of the action this ability to handle what actually happens in the real world. So it's not so much that types can't handle fallibility as naive types can't. And so if you have an expressive type system, you can get there. You probably don't need to follow it, but the bind has been, the combination operator down the bottom has been slightly enhanced to make this work, but it's still fundamentally following the Domino rule. So if you think about what this actually means back in the Domino world, it's a multiplayer game of dominoes, right? Which is, I guess, the fun kind. We knock on the door, and that's fine, but then we have to handle the case, or both cases, of when we try to open the door. So what this says is if the open returns true, we continue on the program and then close it, so we end up in the closed state, that's fine. If it's not the case, if it's false, then we do nothing because the door is closed. So basically what we're saying is, regardless of which domino at the top, our opponent, the real world, the horrible real world where all sorts of things happen, regardless of what domino they play, we can make the line work out. Either, if they play the jam one, then everything works out because we're always closed. Or if they play the open one, then we know that we need to close the door to end up in the right state. So that's the way that at runtime, we've got checks. Because this is definitely still a compile time series of checks, but they guarantee that we've covered all the cases we need to at runtime. All right, so the second one, distribution. One particularly, I think, perhaps underrated invention that exists in the type world is type providers. So I think they come from the F# world, so probably Don Syme deserves the credit for it. In the F# world, they hook into the compiler and I think generate bytecode. So you could actually potentially generate invalid programs in the F# world. But what happens is that they operate on any kind of schema. So if you've got a JSON schema, an XML schema, a relational schema, it's actually a pain to go through that schema and create stubs to statically type it, right? So you have to keep those up to date, you might break them, you just don't really want to have to deal with it because that should be automatically inferred. You've got the XML schema there, why do I also have to maintain kind of a stub file that says what the name of the attributes are? It's kind of just a waste of your time. So what Don Syme realized was that you could do that automatically. So at compile time, it reads in that schema and it generates those types. So Idris also has that, and in fact, in Idris, it's very easy to think about how type providers work because Idris already calculates types. Calculating types, building them, putting them together, pulling them apart is just a normal language feature. So the only thing that was needed to happen to implement type providers in Idris was just to allow that at compile time some of these operations to do some I/O. So I'll show an example. There is a proof of concept that I'll give a link to at the end, but it's a sample text file for what you can do with a vending machine. So it's not written in Idris at all, but I can import those text file transitions that says, you know, if we insert a coin, we can go from waiting to paid. If we return a coin, we go from paid to waiting. The select can fail because there might not be a chocolate in the vending machine. So select goes from paid to either selected or just stays at paid if there's nothing of that item type. And I can consume those types within the program as though I'd written them out in Idris itself. So I do insert coin and I try to select. And this actually can potentially, assuming enough languages get on board with this could potentially help to solve the problem of distributing protocols that can be type checked across a system. Because if you've got, for example, an F# and an Idris system at least, you could potentially generate the same set of interactions that can legally be type checked from the same schema. So it's just an example of how saying that you cannot distribute types when you have a multi-language environment ain't necessarily so. It might be that we don't really have the pieces in place now, but it can be done. Right, so the last thing I wanted to talk about is reciprocity, because there's some really interesting theory here. So I've got a protocol and two parts need to cooperate. If they do the same thing, they'll deadlock. So they have to have complementary operations. So they're known in the literature as session types. So I'm only going to talk about a very brief introduction to it, much simplified. But what session types can do is represent, from a global perspective, interactions of a bunch of actors. So the example I think I read in a paper most recently was around an auction. So there's multiple bidders, there's an auction administrator, and they all have to do the right thing in order for the right outcome to happen. One of the key advantages of session types is they can be projected to local representations. So if I'm one of the actors in this multi-part system, I can do a calculation that gives me an account of what I personally have to do to be on the side of the right and the good. And it turns out that, and this might be slightly surprising, that assuming everyone does the right thing by their local type, you can check and make guarantees about the system as a whole. So an example of where you might want to do session types is, for example, if you have your channel that you're sending and receiving. So up the top, I have session state, and I build it by creating almost a list of types that I send and receive. So I can send is one operation that takes an existing session and chucks a send on the front of it. Receive takes an existing session and also extends it with a receipt of something. Accept and select are interesting because they deal with branching. So accept means I'm going to allow the other party in this interaction to choose which branch we go down in the protocol. So I'm going to allow them to, I don't know, select the cipher or select the use case. So that's actually something that is another example of the non-determinism I need to handle, because I don't know in ahead of time what my client is going to ask of me. And select is if you're the active party in that choice, so you can go down one branch or the other. And finally, there's a constructor for if a session is finished and depleted. So the trick you get for, and this is only for dyadic sessions, I'm not going to talk about the multi-party example here. If you've got two people talking to each other, it's very easy to basically flip the states around so that the person on the other end has the complementary set of operations. So dual is just a function I've written to do that. So the dual of sending an A and then continuing with the session is to receive an A and continue with the session, right? The dual of receiving an A and then continuing is to send an A and continue. The dual of accepting either eeny or meeny is to select one of eeny or meeny. And the dual of an empty or finished session is clearly just an empty or finished session. So what that lets you do is to define the type once and then flip it round to apply it to both the client and the server. So if you think of an addition as an example of where, I know why you would need an addition server, but let's say you have an addition server. It receives an integer, receives another integer, and then it sends the result back. So that's kind of the protocol of states it needs to go through. Negation, well, that just takes one integer and returns an integer back. So the protocol we have as a whole, the calculator protocol, is that we as a server accept, because we've got this wide range of features, we accept either addition or negation as something that we're willing to do for the clients. So if we want to create a calculatee, someone who actually consumes this, we don't need to separately write the types or the series of actions and hope that they're consistent and hope that there aren't any deadlocks. We can generate the types for the client based on what the server has. So the calculatee's type is just the dual of the calculator type. So it's another example of using calculations at the type level to achieve things that you might not originally have thought were possible. So in the end, what it means is that you end up with complementary state machines on both sides of the network. So the one on the left is the server, so it has receives in the place where the one on the right has sends. And so if both sides of that follow the right thing and both sides check their protocols, then we know that overall things will work out. Now, there's much, much more theory in this area, much, much more complex, but that's just a general introduction to the fact that you can have the concept of global protocols and project them to individual roles in a system. So in conclusion, I want to make the argument that we're building systems that we don't fully understand. So in particular in microservice architectures, but not just microservice architectures, that's just the example that I've encountered most strongly. We've got situations where because we're evolving different parts at different rates using different human beings and just communicating what's going on through, I think, mostly narrative, we don't fully understand what's going on. We don't fully understand the implications of the decisions that we're making. We're creating bespoke distributed protocols that manage small pieces of big transactions, and that's really hard, even in the case of well-understood protocols that have been studied for years by people who are experts in it. But we're creating these on the fly. We're creating even unexpected ones that only exist for a short period of time when we've upgraded one part of our system and not another part of our system. So I really think that that's a strong argument I can make for the present, that we don't fully understand the systems we're building. I think that leads you naturally to the next point, which is that we do need better ways of understanding systems like that. We need breakthrough abstractions. We need better ways both to communicate our expectations amongst ourselves and also, ideally, to check that they're right. But it's both of those things. It's not just machine verification that I think is important here. It's also to just get better, to level up at explaining to each other what's going on when we have a big system with many fallible moving parts. And I don't think we do that well at the moment. And I think that it is a fallacy to say that types can't help us once the network gets involved. Like, I think that's a really easy thing to say and a really easy thing to believe. But because of this concept of self-discipline, because of this concept of that types can guide you in all the legal actions you can make and all the things you have to check to make sure that you're adequately acting within this system, I think it's definitely true to say that types can help us once the network gets involved. Now, I'm not making the claim that types are the solution to microservices or anything like that. What I'm saying is that they're a meaningful contribution to the debate and a meaningful contribution to the toolkit. Things like monitoring, observability, there's many other important aspects to making a robust system, but I do think that types are worth thinking about when we're looking about how to build these systems better. So in the spirit of continuing to follow the finite state machine metaphor, this is code mesh, right? So many people are talking about quite similar and interesting ideas, probably in greater depth than I've gone into today. So if you're really interested in the verifying of finite state machines, Oscar is giving a talk about how to apply that to languages you probably are going to be allowed to deploy to production, for example, Haskell. I think his slot is immediately after this one. So if you're interested in the detail of encoding finite state machines and index monads in Haskell, and pure script, then I would go and check out Oscar's talk. If you're interested in dependent types, so the first-class types that you can do all these calculations on, David Kristensen is giving a talk on that this afternoon. And if you're interested in channels and those kind of formalisms around concurrency, I believe that Michael Sperber is giving a talk on concurrent ML tomorrow. So those are the legal transitions to go to from this talk if you're interested enough in the subject to continue. There are many references that I've got here. I've kind of cobbled together my own superficial and beginner's enthusiast understanding of these different topics from many different papers. If you're interested in it, all the links are online. And if you want to follow up on the example of the dependently typed type provider that read in from the text file and generated the types, that's on GitHub as well, in this repository as it happens. Thanks very much.
Thank you, Chris. That was very touching. We have got time for a few questions, if you got any.
Thank you very much.
Sure.
I was wondering, in your experience, how deep, how long are the session types? For example, you gave us the type of the calculator, and you said the calculator would first add and then subtract. But that's actually, it would either add or subtract. So my hunch about session types is that we get pretty simple session types where there is a union of possibilities, then there is a little interaction for those possibilities, and then we go back to square one. Is that so?
I think that's a very good observation, that the sessions that I observe in practice are not long-lived. They're often, for example, just a series of interactions on the basis of a single user request. So they're not often kind of cooperating long-term like that. So it could be scope to request, or possibly sometimes to subsequent actions that are triggered off. So I've seen systems where the single user request is around an application for some kind of financial product or whatever, and that does involve potentially a cooperating series of states that get dealt with asynchronously afterwards, but most are quite brief. And definitely the session types that I think you'd observe would be scoped to a particular request, not, as I've misleadingly kind of implied, a global session where there's a state of a whole system. Does that answer the question?
Yes, thank you.
Cool, thanks.
So you might have to forgive a rather basic question, but it's this. In a situation where I've got an Idris program, which has been written in such a way that my session interaction is modeled, in real life, I'll have something on the wire, some JSON or something, which is the actual protocol itself. How does what you're talking about help me in establishing that what I receive from the other party is well formed?
So if you're asking how do we make sure that what we get from the other party is well formed, it's not so much that you can make sure that it's well formed as that you have a well-defined path to follow if it's not well formed, is the way that you would handle it. So I guess something comes in, it's a blob of JSON, you want it to have all the fields you need for your particular processing, you don't know whether or not it does. You could, for example, parse that and return a sum type that either returns a value or that returns some kind of error. In your finite state machine, you could have a state that said, I receive a string, and then depending on whether or not the string conforms to what I need it to, I go down a success path, or if not, I go down a failure path. And the nice thing about doing it at the FSM level is that you might be able to do things like work out how to do compensating transactions. So if what comes in you can't parse, and that means you need to cancel some other order because you need to restore consistency of the state, you could make sure that if it's not a valid JSON string, you don't just crap out and log, you actually do a bunch of cleanup actions.
Okay. I suppose I was really after, is there any, is there some magic going on here? I suppose that's not the right question.
It's certainly not a silver bullet.
No,
so
okay. So it's not as if I'm having to do less work in order to establish that the input or the thing coming from the wire is
yeah. You're not going to have to do less actual computation work.
Right.
but it does give you, maybe the way to explain it would be, it gives you guardrails for making sure that what you do in the various situations that come into you, that you've covered them.
Right,
that
okay, yeah.
I would say just as a general statement, because as it happens, also being someone from ThoughtWorks, I'm very keen on other ways of verifying programs like test-driven development and so on. But I would say that where types really shine are when you have some types that give you alternatives, because when you've got a combination of many different alternatives, keeping track of all the combinations of those is very hard. So what they do is allow you to kind of have guardrails that make sure that you've thought of the cases you need to think of.
Okay, thanks very much.
Cool.
Sorry, we're out of time. I'd just like to add that if you mean to follow Chris's advice about going to the Oscars talk, that's happening in room 2 right now in about 5 minutes.
Cool. Thanks very much.